Hello, yeah, in this video, time series using R, I want to do some demonstration of those multiple change point detection methods using R. Okay, so the method I'm going to cover changepoint.np, ECP, BCP, MCP, segmented, Rbeast, and wbsts, and change points. First, just let me create the time series. So this is a very simple mean shift time series at 250 location. So the change point package for detecting multiple change point, this is the most basic package. Strength is fast and widely used for standard univariate mean variance and mean variance shifts. Weakness is mainly designed for univariate data and less flexible for complex regression or multivariate data. Okay, so the syntax very easy, just using cpt.mean, cpt.var, cpt.mean var for mean variance and mean and variance detection. Okay, so here you can see a detected change point in the mean at 250. And then mean and variance also at 250. Okay, so capture. All right. So this is pretty quick. And then we go to changepoint.np. Changepoint.np is for non-parametric. So it's non-parametric change point detection, also for detecting multiple change points. So it's non-parametric, so it is useful when distribution assumptions are uncertain. And weakness include often slower than parametric methods and may require more computation. Okay, and the syntax is pretty simple. Just using the npt.np on y and print it out. And you can see down there, the location is 245. Okay, detect one change point. So a little bit off the true value, 250. ECP is energy-based change point using E-divisive or E-agglomerative change point method. Also can detect multiple change point. The strength is handles non-parametric multiple change point detection and can work with multivariate data. Weakness is computational cost can increase for long series or higher dimensional problems. Syntax is pretty simple, using E.divisive, and you have to make the Y, the time series, as a matrix. That's just showing this works on multivariate time series. And just print out the fit, and you can also extract the estimated change point, print it out, and then you can print out the internal, and then you can see there 251. Okay, that's the estimated location of the change point. There's only one. 251 is the boundary value. Okay. Now BCP is a Bayesian change point using Berry and Hartigan product partition model. It assumes normal distribution, then use MCMC for number of change points, their locations, and the second means. Okay. And strength of the Bayesian output gives posterior probabilities of change points, which is easy to interpret. Weaknesses can be slower and more time model dependent than frequency alternatives. Okay, so you can load in the BCP and use the BCP on Y. You get the fit BCP, print it out, and plot it out. So you can see it's quite easy to read the output. You can see here. The numerical one is you got this matrix printed out. The first column is the time point. The probability is the posterior probability of change point. The x1 is the mean change, okay, mean shift. So if you go down, so it's almost like 0 until you hit 250. For going from 250 to 51, you got 0.598. That's a huge spike of the posterior. So 251 is kind of the change point. Okay, and on the right hand side you can see the graphs. It shows you the original data and the fitted line showing the mean shift, and also the bottom plot showing you the posterior probability of change points. Okay, All right, let's go to MCP, which is Bayesian segmented regression with multiple change points. So strengths flexible Bayesian framework for piecewise regression and structural change point models. Weakness, the model specification is more involved than simpler change point functions. So this is not really for time series, but more for regression models with breakpoints. Okay, but we can use it for time series. Let's see how well it works. Okay, so in order to use this, you have to install the JAX package, which is just another GIF sampler. I provided the URL there. You have to download JAX from there, and then you can load RJAX, and then you load in MCP. You have to put the data into a data frame, and you specify a model with a list of Y tiered 1 and then tiered 1. So you compare two piecewise linear models, and then you use MCP to fit the model using the data and the parameter of x equal to time. And then you can print out the summary. You can see down there it's computing. Since it's using MCMC, it's going to take a little bit of time. Still going. Okay, now you have seen that. You can see the CP1 is 249.45, so pretty accurate. And on the right-hand side, you can see the original data points and then the fitted lines and then the change point posterior probability. Okay. All right, the next one is segmented. There's another regression model with breakpoints with possible random effects. So this is even more general than the MCP because this can include random effects, which means that it can be applied to longitudinal data. Okay. So its strengths, whether useful for breakpoint estimation in regression models and easy to interpret. Weakness, more appropriate regressions breakpoints than general time series change point detection. Okay, so the loading the library and then you have to fit a linear model y regress on data a time, and then you refit it, the linear model fit using the segmented, and you actually tell R you want at the position the PSI equal to 50, and then you print out the estimation. You can see there the time, the breakpoint is estimated 388, which is far off from the true value to 50. On the right hand side, you can see the segmented plots. So it's really not accurate. So this just tells you this function is not really good for mean shift of stationary time series data. Just keep that in mind. Okay. So the Rbeast is Bayesian estimator of abrupt changes, seasonality, and trend. Okay, so this is pretty comprehensive. So it's a Bayesian, use the Bayesian ensemble model averaging method for time series decomposition and change point detection. So when we talk about change point, sometimes it's complicated because time series can have seasonalities. As there's seasonal change points. Okay, so those are not the structural change points we're detecting. Okay, but this one is really handles all the change points. Okay, so the strength is strong Bayesian framework for change point detection and time series change decomposition done at the same time. Okay, weakness, heavier output, and a steeper learning curve than simpler packages. So you can load it in, use the beast function on Y, and just print out the fit, and you can see it has a tons of outputs. You can see it has probability of so this is MCMC. It has a plot of probability distribution for number of change points. You can see there's a 1, 2, 3, and 4, and 5, 6. So it has detect the multiple change point there, but some are like really structural change point, and there are some are seasonal change point. Okay, so there's about 4 seasonal change point, and then you have the this is the structural seasonal change point. give you the probability of seasonal change point and their locations. And then you have the plot probability distribution of number of change points. These are the structural change points. You can see for 1 it's very, very high. Then there's a 2, and then and 3 is dropped very, very largely. Okay, so it goes to give you the locations at 251 with a very high probability of change point, posterior probability. Okay, and if you look on the right hand side, the first above, that's the raw data with the fitted curve showing the mean shift, and with the gray area as the confidence band. And then the next one is the spike of posterior probability of seasonal change points. There's showing about 4. And then the next one is the posterior probability of structural change points, about 2. Okay, and they are around 250 to 51. Okay, so this is a very sophisticated change point detection method. Okay, all right, let's go to wbsts, and this is the multiple change point for non-stationary time series using wild binary segmentation and locally stationary wavelet model. So mathematically complicated. Let's see how well it works for this case. Okay, so it's actually does not really work. It doesn't really plot the vertical line for the change point location. Okay, so it doesn't work for this method. It mainly for non-stationary. For change points, it's a collection of change point detection method using dynamic programming with L0 penalty and cross-validation for toning and local refinement of estimate change point. Also mathematically sophisticated, provides collection of change point collection method for one package. Okay, and weakness may have a smaller user base and fewer examples methods. And let's just take a look how it works. Okay, so first we did the data, and you set the gamma set and do the cross validation, and then you pick a gamma with the lowest errors. Then you can use the local refinement, and then you do the plots, and you go through all this trouble. You get hey, this time it worked. Univariate mean change point packages. Okay, so basically what we learned: practical selection guide strengths. This guide to choose the package based on the data type and analysis goal. No single package is the best for all change point problems. Okay, so use changepoint for strong default choice. Use changepoint.np as ECB for non-parametric detection. BC fancy Rbeast for Bayesian changepoint modeling. Segmented for regression breakpoint rather than general time series detection. So changepoint detection is a very difficult topic. Okay, so we have demonstrated multiple packages here. You can actually run a small simulation study to compare different methods, and also you may try some, say, assemble method, maybe by combining multiple change point methods. Sometimes they work, sometimes they still don't. So basically, change point detection is a very difficult problem. Okay, thanks for watching.